Okay, so we've now arrived at our next to last major topic of the semester, which is systems of equations. So we've already looked now at linear functions, right, in two variables. So now what we're going to be doing is looking at what we call systems of linear equations, which are for us going to just be two equations containing two variables. So a simple example of this would be this little system here, and I actually made the mistake of not including that little squiggly brace there, because when you include that little squiggly brace next to those two equations, what you're doing is you're kind of tying them together, and that's indicating that they're not just individual equations, but that they represent a system of equations. Okay, so you use that little squiggly brace there to indicate that they're tied together, so we're considering this a system of linear equations. So if we look at these two equations individually, y equals 2x minus 4 and y equals negative 3x plus 6, we can see that each of those equations, if we graphed it, would be a line, right? And then each equation is going to have many ordered pairs that are solutions to it. So for example, like the top line, all right, well, the y-intercept is 0, negative 4. So the top line, 0, negative 4, is a solution to it. And then if I plug in 1, I get negative 2. So 1, negative 2 is another solution to it, right? For the bottom line, the y-intercept is 6. So 0, 6 is a solution to it. Then if I plug in 1, I get negative 3 plus 6, so I get 1, 3, right? So on and so forth. So they each have many solutions. In fact, an infinite number of solutions. However, unless the two equations represent the same line or they're parallel lines, they will have only one point in common. And that's what we're going to be searching for, the one point that they have in common. And that one point that they have in common, which we might call the point of intersection, it's going to be the solution to the system of equations. All right. So one way that we can find a solution to a system of equations is just do it numerically, which is basically just guessing and checking, plugging in values and seeing what works. So as we did before, right, when we plugged in 0, we got negative 4 for the first one and we got 6 for the second one. Then when we plugged in 1, we got negative 2 for the first one, and then we got 3 for the second one. When we plugged in 2, we got 0 for the first one, and then 0 for the second one, and that's key. Then you plug in 3, you get 2 for the first one, and negative 3 for the second one, and then you plug in 4, you get 4 for the first one, and negative 6 for the second one. So you can see here that when x was 2, in both cases, y was 0. So that's the one point that these two lines have in common, right? The one point that's a solution to both of these equations, which is the solution to the system, which is the point 2 comma 0. Okay, so that method that I just used there by filling in a table is actually called the numerical method, which we had discussed, earlier in the semester when we did the 4 ways of looking at input-output rules. And that's a valid method. It's just one that you're generally not going to use much in this class. So the first, formal method that we're going to use to solve systems of equations is going to be by graphing them. And graphing them is very easy, right? We just did graphing. So what you do, you just graph both the lines and you find out what their point of intersection is. Okay? So again, I forgot to tie these together. I should have tied these together with a squiggly brace, right? That's a system of equations. So I want to solve that. So what I would do is I would say, all right, well, the first one has a slope of negative 1 over 1 and a y-intercept of 4. So remember what that meant. That meant I'm going to start out at 0, 4. And then from 0, 4, I'm going to go down 1 over 1 and keep repeating this process. And then when I connect, I end up getting that straight line there. And then I'm going to do the same thing with the other line, right? The other line has a slope of 1 over 1 and a y-intercept of negative 2. So I'm going to start at 0, negative 2, and then I'm going to move up 1 and right 1. So I started at 0, negative 2, up 1, right 1, up 1, right 1, up 1, right 1. You can see right there that's where they're going to cross. But I should draw the line in, and when I do, I can see that they cross at that point right there. And what is that point? It's the point 3, 1. So that's my solution. And of course, after you do these, you can do checks on them, right? Just make sure that the point 3, 1 satisfies both these equations. 1 equal to negative 3 plus 4. Well, 1 equals 1, so that line checks. And is 1 equal to 3 minus 2? 1 equals 1, so that line checks. That was a very simple check. They're not always going to be that simple. But you have to check it in both equations, make sure it satisfies both. Okay, so then here's another one. Now the difference with this one is the lines aren't in the y equal mx plus b form, so I will get them in that form first. So if I take this and subtract 8x, I would get 2y equals negative 8x plus 12, and then I would divide everything, right, by 2. So I'm going to end up with y equals negative 4x plus 6. So the slope is negative 4 over 1, and the y-intercept is 6. So that means I'm going to start at 0, 6, which is all the way up top, and then I'm going to go down 4 and over 1. Down 4 and over 1. Down 4 and over 1. So I can connect those 4 points, and there's my one line. So now I do the same thing with the other line. Y plus x equals 0, that's an easy one to solve, right? I just subtract x, so I end up with y equals negative x. But remember, that just means the slope is negative 1 over 1, and the y-intercept is actually 0. So I'm going to start at 0, 0, and then I'm going to go down 1 and right 1, down 1 and right 1, down 1 and right 1, and I can already see what the solution is. But let me graph, and when I graph them now, I can see that those lines cross at that point, which is 2, negative 2. So that's the solution, 2, negative 2. And that should check in both those equations. Again, I didn't tie them together. I should have tied them together to indicate that they are a system of equations. I'll try not to forget that moving forward. So another one here, this one also we have to now put into the y equals mx plus b forms. So we have 2x minus 3y equals 6. So I'll subtract 2x, and I'll have negative 3y equals negative 2x plus 6. And then if I divide everything by negative 3, just watch your signs here. This becomes y equals positive 2/3 x minus 2. So my slope is 2/3, and my y-intercept is negative 2. So I'll start at 0, negative 2, and from there I'll move up 2 and over 3, up 2 and over 3. And remember how we had talked about this when we graphed the first time? Instead of going up 2 and right 3, I could have also went down 2 and left 3. Again, you just got to make sure that you're continuing the line, right? And you are. You're continuing the line, so I'll graph that line. So there's that one. And then the other one I'll do a similar thing on. 1 minus y equals negative 2/3 x. So if I subtract 1, I would have negative y equals negative 2/3 x minus 1. And I will divide everything by negative 1. And this will now become y equals positive 2/3 x plus 1. So my slope is 2/3, and my y-intercept is 1. So again, my slope now is 2/3, and if you remember what happened with that is, we had said this last time, when we have lines with the same slope but different y-intercepts, they're going to be what we call parallel lines. So if I plot 0, 1 and then move up 2 over 3, up 2 over 3, and if I move down 2, left 3, I'll see that these lines are not getting any closer together, right? And if I graph that line, I can see that those lines are never going to cross. So actually, this system of equations has no solution, right? And that was something that I noted at the beginning, right? We had said unless the two lines are parallel or they're the same line, there's going to be exactly one solution. So this line, in this system, the lines are parallel, therefore there's going to be no solution, right? And sometimes you see this written as that little symbol there, which is just the symbol for the empty set. But for our purposes, we can just write no solution. That's perfectly fine.